Welcome back to Calculus 2. Section 4.4, the Logistic Equation. We're going to go over 3 different topics. We'll do a review of population growth, talk about how the simple model is deficient and how the logistic equation remedies that, and then we'll walk through the solution to the logistic equation. Let's get going. In a previous assignment, you had a separable equation in the form of y prime equaling k, constant k, times the unknown y. That equation produces an exponential growth model for population. If we add in an initial condition for the population being some initial population, setting up the rate of change of the population is proportional to the population present, is an initial value problem for short-term population growth. Now, if you think back what the solution looked like, you would have found that the solution is that the population at any point in time is the initial population scaled by an exponential quantity. We can write down that the constant k is termed the growth rate when the growth rate k is positive. Thinking about the exponential function is an increasing function if you just take e to the t, leading to growth. If you take the k to be negative, you wouldn't have a growth exponential, you'd have a decay exponential. In the case of growth, this exponential, what does it do? It grows exponentially. That's a colloquial phrase. And then it grows without bound. And thus, this IVP produces a solution, which is a model for population, but that model is only relevant over a short term. That the population must tend to infinity, according to this model, doesn't jive well with realistic situations. So we have a shortcoming to the model, and we want to remedy that. Now, here we're looking at a typical type of assignment dealing with exponential growth. So go back and review this type of algebraic manipulations. And then let's move on to the logistic equation. Okay. So we have a direction field for the exponential model that the rate of change of population is proportional to the population present. In the direction field, we have a particular solution sketched out that might correspond with an initial condition where P naught is a positive quantity. In terms of the model for population, it does not make sense for P naught to be negative. However, mathematically speaking, we can set up an initial condition for P naught being negative, and that we would produce solution curves which would asymptote to negative infinity, leading to the notion that the equilibrium solution, p equals 0, is asymptotically unstable. Recall that the equilibrium solution is the notion of there's no change in the solution. So dp dt, the rate of change of the population, being 0, there would be no change in the population. If you start with no population, then you have no population. Now, let's introduce a new idea called a phase line that for any equilibrium solutions, we could make a dot and then draw arrows away from the dot to indicate the direction of asymptotic behavior for solution curves. So in this case, the equilibrium solution, p equals 0, is asymptotically unstable. We have two arrows, one going up and one going down, away from the solution. All right. So let's get into talking about the logistic equation and what we mean by logistic growth. So the rate of change of the population is the product of now two terms. Notice that we have the exponential growth factor, Kp, and then a second factor, which is a binomial. It's the difference of unit 1 and the current population over capital K. Remember, lowercase k. It's the growth rate. Capital K, new term, is the carrying capacity. Think about a situation where you're going out shopping. Maybe at some point in which you're purchasing a large purchase, a home, a car. Maybe it's a less large purchase, a phone. Maybe it's just the weekly food shopping. Any of these situations, you have an idea of a budget, what you're comfortable with. Same notion can be applied in a population, that the environment in which the population resides is going to have a large determination on the size. And we can term that, capital K, the carrying capacity. So that if the population, P, is close, near the carrying capacity, this quantity would be approximately 1, and 1 minus 1 is 0. Let's take a look at the direction field then, so that we're coming up with an equilibrium solution, P equal K, in addition to the previous equilibrium solution under the exponential model, P equals 0. Two factors, the exponential factor and this difference. Now, we have drawn in a solution curve for a P naught taken between 0 and carrying capacity K. And we can see that when, if we assume that this P naught is a small quantity, that when you have a small population, the population is just getting started, you can essentially ignore this difference term because it would be 1 minus really small, which is essentially 1. And then the population will behave according to an exponential growth model. Thus, if we truncate time over a short term, we are looking at a curve which very much resembles exponential growth. But as we noted, as the population gets closer and closer to the carrying capacity, this difference becomes closer and closer to 0, or in other words, that exponential growth rate is capped and tends to slow down, and the closer and closer population becomes to the carrying capacity, the slower the growth rate becomes. Good. Now, let's go back to this idea of a phase line, that we now have two equilibrium solutions. And from this direction field, we still see that the P equals 0 equilibrium solution is asymptotically unstable, but that P equal K is an asymptotically stable solution. Take a note that from the direction field, if you took a population which is larger than the carrying capacity as your initial population, that values P would be larger than K. Thus, the quotient P over K is bigger than 1. The difference is therefore negative. Population being positive, this right-hand side would have a negative value, and the rate of change of population is negative, i.e. decreasing. Very good. That's the logistic equation. We're now going to look at the derivation for the solution. Okay, so we'll start by writing down the logistic equation. The rate of change of population is equal to the growth rate times the population times a product, times a difference of 1 and P over K. All right, we're just going to do some algebra. Rewrite the 1 as K over K, carrying capacity over itself. More algebra. That allows you to then factor out that common denominator. Factor off the capital K. Now, take a look where we have a differential equation for an unknown P, and P is taken as a function of T. The K and the K are each constants. Thus, we're looking at a separable equation. Separate out the variables. We'll keep the lowercase k just for convenience on the right-hand side. The right-hand side, when we integrate, is going to be an elementary integral. On the left-hand side, we are integrating with respect to variable capital P. Capital K is a constant. Thus, this integrand will benefit through partial fractions. So if we apply partial fractions, we can recover simple integrands. The first one is elementary. The second one requires a u sub. In the second integrand, notice that the minus is appearing on the variable of integration. Each of these integrands will result in a natural log. But because the denominator in the second term has a minus on the independent variable of integration, we're going to get a difference of logs. Right-hand side again is an elementary integral. Evaluates nice and easy. Only need to introduce one single constant of integration. We can do that on the right-hand side. Left-hand side, let's combine through properties of logs the difference of these two logs as the log of a quotient. And we're trying to solve the logistic equation, which is an equation for population. So we want to solve this equation in terms of P. We can do that by exponentiating both sides. If we exponentiate both sides, we'll remove the log from the left. For the moment, keep the absolutes. The exponential of a power, which is a sum of terms, can be written down as a product of exponentials. Left-hand side, since we know that the absolute of a quantity is non-negative, and since we know that the exponential of a quantity is always positive, let's reterm this arbitrary constant, which is always positive, but allow it to be positive or negative. Term it C prime. By allowing it to be positive or negative, we can remove the absolutes from the left. All right, so C prime is an arbitrary constant, which may be positive, may be negative. All right, again, we're trying to solve for P. Now we just do some algebra. Cross multiply, distribute. Right-hand side becomes a difference of two terms. Recall our objective, trying to solve for P. Collect all the P's on one side. Factor off from those two terms. Now we just have a single p appearing in the equation. We can therefore easily solve by removing the coefficient. That's accomplished by dividing by that coefficient on both sides. Very nice. This is the general solution to the logistic equation. If we set up an initial value problem, here's what the solution will look like. It's what we just established. In this assignment, you want to verify that the C prime is given by this quotient. You want to verify this. And then after verifying that the C prime takes this form, then go to the solution P of t and show that P of t, instead of written out in C primes, P of t can be written out as this second expression. So it's just plugging in and doing algebra. Good. So 2 parts to this assignment. Next, do a little bit of analysis. If you go back and you look at the logistic curve, it begins by appearing as an exponential growth curve, but then starts to flatten out. Then that introduces the notion that at some point there is a fastest growth rate. When does that occur? Well, you're therefore trying to find when is dp dt a maximum value. So in this assignment, you're trying to find a max value. Excellent. So there'll be some Calc 1 computation, and then after that, a little bit of algebra. Very good. All right. Then here, this is just an assignment where you can use the form of the particular solution to the IVP for certain values of growth rate K and carrying capacity capital K. And then having that particular solution make a prediction. All right. A fun assignment is to go back and look at our derivation of the particular solution for the logistic equation. Follow it to come up with a solution to the Gompertz equation, which is that the rate of change of a population is equal to a constant alpha times the natural log of the carrying capacity over the population, product the population. Okay, use Desmos to draw direction fields. You can assume that K is equal to 1. And then compare that direction field with the direction field for the logistic equation. And then finally, come back and do the analysis, analytical computation to come up with the solution P of t. Very nice. That is a brief overview on the logistic equation. Thank you so much for watching. Please like if you find these videos useful, and I will see you on the next one.